All right, so thank you everybody for a bit of patience. So now we can start with the event itself. Welcome to the 27th PyData Trójmiasto event. We're very happy to have you here today. To say just a few words about the PyData itself, this event is a local branch of multiple events happening all around the world. So everywhere where you go, you can imagine that organizers are organizing the talks more independently. The talks are different, but all is focused around artificial intelligence, data processing in general, and our not partner but parent per se is NumFOCUS Foundation, which is the foundation that supports multiple open source projects like NumPy or SciPy you might be familiar with. The event wouldn't happen without a lot of companies who help us and people from these companies that stay behind each contribution. So first, thanks to Gdański Park Naukowo-Technologiczny for hosting us here, to Pomeranian Special Economic Space for also combining the whole possibility to host us here, for CodeMe Foundation as well, and Interizon. We encourage you to check out the CodeMe Foundation events happening in Gdańsk. Wenke, who's today's pizza sponsor, they're looking for Python developers. If you want to know more details, then you can talk to me as well. Gradient is a local academic club, so they're more focused into very in-depth workshops, which they will be starting soon in November. So there will be workshops that are regular on Gdańsk University of Technology, and last but not least, our monthly local Python meetup, PyData. They will have their event also next Monday, I believe, 30th of October. We have a Discord group, was created a month ago, so you're still welcome to get into the group itself, where we discuss different topics. We haven't discussed too much, but I hope you'll have good ideas for contributing to PyData or any kind of initiatives you would like to extend. Leave us a message just as an ending note for introduction to PyData itself. There are different channels you can find us through, and let us know about any kind of things you'd like to let us know about. Not to say that if you have an idea for a presentation to give a talk, then just leave us a message. Today we'll be having two presentations. The first one with Wojciech Janowski from VoiceLab about language models. The second one with Łukasz and Piotr from Snowflake after a little break. So a quick introduction. Wojciech works as an NLP researcher at VoiceLab and is pursuing PhD at the Gdańsk University of Technology. And let's welcome Wojciech with a round of applause.
Okay, it's work.
just once again. Right.
So, okay, hello, I'm Wojciech Janowski, and today my presentation is about language models. This is a very fancy topic, I think. So let's start. So this is I'm PhD student at the Gdańsk University of Technology. I'm working at graph modeling, real human conversation. And of course, at VoiceLab, I'm NLP engineer. I'm working in very fun and amazing NLP team. And we together working about Trull. This is our first Polish large language models created by us completely. Not from scratch, but we fine-tuning. So let's start with basic introduction, what this presentation will be about. So we have large language model. For example, ChatGPT is the famous one. And for many people, these models work like some magic box, magic stuff. In the input, we have some instruction. This is written by me, simple, write a short poem about this. And ChatGPT produced this beautiful poem. It's amazing for many people, but not many people know how the models work. And today I try to explain this. And I hope at the end of presentation, you will never treat this model like magic box, but something rather than complicated, but known machinery. So first, let's start from basic definition about language model. What is language modeling? And this is simple concept about modeling language. This is how NLP part. Many tools like TTs, SR uses in some cases some variants of language models. Concept about language models was introduced in 80s years, something like that. And its task is, it's simple. It's a probabilistic model of a natural language. It could be any language, Polish, English. Today exist multi-language models. But language model produces probabilities of a series of words. This is a simple task. As an input, we give some words, some sentences, and language models produce probabilities of these words. That's simple. Before artificial neural networks, language models was built from many basic statistical tools. Today, any language model is neural network. And language models is trained in the text corpora. Basically, it's only big data set of text. It could be books, articles, any human written text. And today, modern neural networks, big neural networks like transformers with enough parameters can work like ChatGPT. So in the concept, ChatGPT models is normal language models, but much, much bigger. So when language model is large, it's a tricky question. And we don't have any precise definition about when large language model is large enough. So I show you a simple table with model sizes. At the top, we have bird-based model. It's not too much, but not too big transformer architecture model created by Google a few years ago. And this kind of model have around 100 million parameters. Llama version 2, this chat GPT killer made by Meta, open sourced in version 2. This kind of model have from 7 billion to 65 billion parameters. As you can see, it's much more than 2 million parameters. And GPT-3 have around 175 billion parameters. GPT-4 is enormous, is quite bigger, but we don't have precise knowledge about how GPT-4 works. But GPT-4 is much bigger. ChatGPT is version, some kind of version about GPT-3. It's called GPT-3.5 Turbo, something like that. And
it still will be a LLM or it will be ELM?
This is only naming. You can name it whatever you want. Something clicks tell that GPT-4 is a couple of smaller models, experts models working together. But OpenAI don't publish any more details about the technical stuff.
What might be the cause for the Google's model to be so small compared to the other ones?
Today, because BERT model was released earlier, few years ago, it could be called preprocessor of GPT models. Newer Google model BART is, I don't know precisely how big is BART, but it's around size of GPT-3. But I don't know precisely weight. So this diagram shows what language model do. As I said, we input some sentences. It could be one sentence or whole text. And as an output of model, we have something magic value of some fancy function called perplexity. This is function that measure how good the prediction is. And the relation is that if sentences is more correct, then perplexity of this sentence is lower. So if we throw to the model not very good sentence, we have bigger perplexity. And perplexity uses distribution, probability distribution generated by the model. So this is simple language model task. So why we use probabilistic distribution? More precisely, the discrete probabilistic distribution. And if we think about language, we can assume that each natural language has some rules, grammar, inflection, etc. Some languages have more complicated rules, other languages are simple. And some words come on occurs together. We have some phrasal verbs, and etc. And if we think about it, we can assume that based on these facts, we know that's correct sentence. Then if we're talking or reading, we can accept that we probably read correct sentence. So we can describe a set of words by its probability. We can assume that random bag of words will have much lower probability than well-designed sentences. So if we analyze big enough text corpora, we can create, based on this data set, some language distribution. We can predict based on this text corpora, what sentences is good and what sentences will be bad. And language model learn the text distribution, language distribution based on training data set. And the last point is very important, that every language model can properly predict only a subset of language, because models learn from the text training data set. So if we ask model about specific subdomain language like medical or insurance, the model that never see this kind of data can make some useful predictions. So this is very important note. So next question is, why language model have a dictionary? Because dictionary is very important part of the model itself. So language model only use known elements. The language model must know the words that they're predicting. And set of these elements is called dictionary. And in other words, model learns to map input words from dictionary to the feature space. It's because every neural network transform inputs to the numbers, precise vector of numbers. So language model at the input transform input words to the vectors, very big vectors. And if we try to model the whole language, if we want to know bigger number of words, the more words model will predict. However, there's some problems with that, because it's something from math called the curse of dimensionality. With growth of the dictionary, our neural network requires exponentially more data to learn. And this is a huge problem. So let's dive into what is that element of dict. It could be word, tokens, engrams, and I describe this. So we have two possibilities. We use in the dictionary small elements, like letters. The letter is the smallest number of the language, written language, it's letter. And if we have small dict, we have much more data to train the neural network, because if the elements of the dictionary is small, one letter doesn't have any meaning in the context of language. So we must use much more data. And letters language models are not used very often. They are very fancy, and that's all. On the other hand, we can use large elements like engrams. Engrams is a bag of words, simple. And it's easier to learn language distribution, because if you have few words, we have easy to learn about the language from these words. But dict is much bigger, because what if we can model improperly written words? We must use it in the dictionary, so our dictionary will grow and grow and grow. So we must find the sweet spot from the language and from the dictionary side. So we use tokens. Tokens is the sweet spot for language modeling. And what is token? Token, it's simple, is subword. It's part of the word. Oh, we have this table, and first we have split text to the word. Second, we have split text to the letters. Then we have text split to the subwords, tokens. And at the end of the table, we have example of bigram. So it's n-gram in size of 2. So we packed our sentences to the small part of the word. And the best solution for language modeling is we use two subwords. And this is called tokenizers. Tokenization is important process of pre-processing text. This is the first steps in the language model training. And today we use most common two algorithms to divide text to tokens. And this is byte per encoding and sentence piece. Of course, there exist many other algorithms, but this is the most common. And next chapter is about token predictions. It's called next token prediction. So we have our language model. Our language model can describe distribution of words. It produces probabilities. It's very fine, but pure probabilities is useful. We want the model to generate next words, to follow us our prompts, and what we must do. We use something simple algorithm called next token prediction, and this is the main process for the text generation, and it's commonly used by LLMs. And this algorithm utilizes probability max by the language model. And the definition of this task is quite simple. So if you have set of tokens already produced, or these tokens can appear as the input. So our goal is to predict next token. So we can do it by maximizing conditional probability of the based from the previous token. So based from the previous list of tokens, we generate next tokens. And this is simple chain rule. We can do it forever. As you can see, this is a simple diagram that shows how language model produce new tokens. So as the input, we have our input sentence. It could be prompt or something like that. And every model has some limits called context window. Every model has some constrained size of the proceeding context. Some models have larger, some models have smaller context. But the models read and extract information from input sentence. Then models itself produce tokens probabilities. And from these probabilities, we can read and generate next token. And this is done by decoding algorithm. And simple algorithm is, of course, maximizing probability from each token. And this algorithm decodes tokens probability, which is, in other words, list of possible next tokens. And after the coding process, we have next token. And we add this next token to the input. And we have new input, and we go on forever. We can go it forever. We can generate token by token answer to the question given by the input. So this is example of the coding. And we start from prompt, are you hungry? And first we will decode I. And you can see the numbers of the probabilities of existing of the next tokens. As I can speak earlier, we have many others algorithms to decode. This is algorithm with temperature. Yes.
Every step, the whole dictionary is used to the TN, or just a subset of the dictionary?
Yes. In common pattern is to use the whole dictionary, and more precisely, this distribution of words is distribution from dictionary words. So probabilities from all tokens from dictionary is sum to 1. Like probabilities should do.
But actually, in modern GPT models, you also have dynamic softmax, so you only use a part of that dictionary to generate predictions, so the training process is faster and
Yes.
the inference is faster.
Yes, of course, exists some variants of optimization. And this is example of decoding with temperature, and this may add some noise to the output because we pick, not often we'll pick the most probability word, but one of the top probability. And this adds some noise, the output, and some randomness, because sometimes we want that model will produce correct output, but with some randomness. And this is the simplest way to add some kind of randomness to the output. So we proceed token by token. For example, of course, this is an example, and I use words because words are easier to read. So step by step, we decoding and asking model about new tokens, and we have complete answer. I would eat something. But the next question is how we stop the generation. Yes.
Another question. So when you talk about noise, is this the temperature, or is it the noise concept is something like the temperature? Like not the first most probable word is always chosen, but
This is only simplified example. It's plenty of algorithms that add noise. It's temperature, it's top K, top P parameters. But this is the simplest way to show that we not always choose the most probability one. This is some simplification. And the next question is how we control the generation process, because sometimes we want to stop the generation. How we tell the model that stop, this is enough. We can of course force the model to always generate, for example, 500 tokens or generate maximum number of context window, but this is not very useful. We want to model that model somehow know that when he should stop. So we add the dictionary control tokens. This is the easiest way. We have, for example, begin of sequence token and end of sequence token. And we learn model that when he should end the generation. So at the beginning of the sentence, we always add the BOS token, begin of sequence. At the end, we add end of sequence token. And through the training process, the model learn when it should stop the generation. And this is the simplest way to generate text. So now I show you the basic steps to train large language model from scratch. And the first step is to prepare enormous amount of text, because our model is very large, billions of parameters. we must prepare lots of text to fit the model, because if the model grows, we need more data to train the model. So if we need more data, we must use lots of GPUs. So we must rent a GPU cluster, and this model can train from scratch for weeks, months. It took very long, because we create from this text books. We call it self-supervised, and we must create training samples for next token prediction. And what is the sample? So our model wants to know the language, learn the language. So we must create many examples from each sentences. We create basic n-grams as the input, and targets will be the next tokens. So as you can see, we from one sentence create few examples. We can from one bunch of text we can create dozens of examples, because we must fit the context window. So we have exponentially more examples created from simple short text. As you can see, these create enormous data sets. So that's why the language model training from scratch took very long time. So next step, it's called fine-tuning. It's more fun, it's more enjoyable, and we at the VoiceLab focus on fine-tuning the large language models. So what's the fine-tuning? So that we use pre-trained models. We call it pre-trained models, because training model from scratch is not funny. We don't have resources, we don't have time, we don't have enough GPU powers. So we start from Hugging Face repository. There are plenty open source models. As I call Ariel, we use, for example, Llama from Meta. And we can download this model and start our own experiments. So we call it precise instruction fine-tuning, because pre-trained large language model can predict probability of the input sentences. He is doing very well. He can generate simple text. He also has some kind of knowledge, learn from the data set. He has some knowledge about language itself. Model weights contains some information, but this model cannot follow user instruction. If we test raw large language model, for example, raw Llama, that model can generate some simple talks, but cannot follow our instruction. We want that our model follow user prompts instruction and generate whatever we want. So we call must fine-tune. It's called instruction fine-tuning. The main goal of LLM, as I said earlier, follow the user instruction. So user interact with model by chatting. For example, we have ChatGPT demo, and we can chat with him. And this is the next step of training. And we must train on instruction dataset. And instruction fine-tuning will teach our model how to follow the user prompts, how to generate what we want. And this is the most important step in evolution process of language modeling, because we change from simple text distribution, language distribution, and we jump to the intelligent assistant that can understand what we want and generate whatever you want in simplification, in some simplification. So this is the most crucial step for our proceeding. And what is instruction? Definition of the instruction is very simple. It is some kind of prompt as the input, and it could be task for extracting, generating, calculating. It would be everything. And the second part of the instruction is the correct output of the model. So if we have example of please that calculate the area of the square rectangle 4 by 5, and the model should answer that is 20. And this bunch set of instruction is instruction dataset. And funny is on the low level, the training of the language model is the same. It's still on the low level is next token prediction. But in our abstraction, you can call it a new abstraction layer, we are one step above. And this is not simple text, but instruction and outputs. And we must prepare many of instruction. And it's some problems with this dataset. But we have some fine information. Fine-tuning on instruction requires less GPU because we have small dataset. And for example, we can fine-tune on few GPUs. There exist algorithms that optimize training or training some parts of model. So we can train at home or small business or rent few GPUs for few days, few weeks. But it's one problem, creating of these data sets. The raw language model was trained on the pure text, pure corpora. We download the Wikipedia, we scan the books, and we have data set. But with instruction, we must prepare instructions and outputs. And data preparation is challenging problem. It's a whole data science. This is the most time-consuming. Preparation, correcting, and checking the data sets. We spent all these weeks, months, and of course data collection and annotation, because we call this process annotation. It's expensive in time and human resources. So on the one hand, we need less compute power, but on the other hand, we need more human manually work. And let's dive into these data sets. Because we use very often open source data sets because we don't have an efficient number of humans to create data sets. So we use internet and download open source because open source is fine. But we have some problems because large language models are sensitive to bias in data. Any small perturbation can have influence, negative influence, or our model performance. I show you a few examples, but I think every data scientist knows that open source data cannot be trusted. We must always check everything because we have unexpected behavior of models. So as an example, I show you, this is from Alpaca. It's Alpaca dataset. And we find that dataset contains some mistakes, and the model from this can learn nothing. And if we have I say around 100 instructions, and few hundred will be this kind of nothing less. Our model can predict garbage, so we must check and correct every this kind of mistake. The golden rule is we want less data, but with higher quality over numbers. It's a good point. So this is another example of incorrect instruction. Sometimes in open data sets exist nonsense instructions. I don't know why, but we must correct it. So if we work on the rule, the main part of the production process was to correct and find. Correct is easy, but we must find these mistakes. For example, earlier version of our model, if the model don't know the answer, it will generate that he cannot translate it to other language. And we think, why? Why if he truly does not know the answer, then ask for translation? Does not make sense. And we find some data set from open source that this data set contains lots of misannotated translation tasks, and our tool was biased on this data. So we find it after 2 weeks or 3. So this is hell of data. So do you have any questions?
Yeah. Can you use stronger model to create training data set for fine-tuning for a weaker model?
Yes, this is quite new approach. It uses GPT-4 because GPT-4 is the best. And on the other hand, it's a good idea to use something better. But always you must remember that every model has some bias. Sometimes GPT-4 can produce not the best output. We always must checking the answers. Of course, use stronger models speed up the process, but we never treat the GPT-4 as the absolute. And so what if OpenAI wants to produce better model than GPT-4? Creating data to train better model than GPT-4 based on GPT-4 output could be misleading. Yeah?
You fine-tune the llama and the polish instructions?
Yes, we have our own data sets, conversation data sets. We create data sets from internet. We create our own Polish data sets of instructions, and we we also change some data sets existing. We convert from one tasks like translations data sets or sentiment to the instruction data sets.
So the llama model is like multiple languages internally. So how do you make sure that these distributions do not mix? So you get like outputs in different languages.
We always add some general data sets. It's true that if we train a model on small domain data sets, the model could forget information from previous trainings. So we always add general purpose data sets. And during training, we often check the model performance. So we know exactly when the model starts to degradating. And that's it.
Last question.
But you use original Llama English tokenizer, yeah?
Yes, yes.
So we can code through Polish language model if we use original English tokenizer?
Llama uses multi-language tokenizers. Llama itself is multi-language. It's some part of Polish data, but I think 80 to 90% of data is English. Raw Llama can produce Polish language, but often the model makes mistakes because Raw Llama uses I think sentence piece, and the tokens is more general than words, and the tokenizer is multi-language because they use tokens from every language. They add, I think, the Chinese and the special tokens they add.
Right, so let's thank Wojciech for the presentation. With all the points.
So thank you, and join our Hugging Face, VoiceLab Hugging Face. You can join our LinkedIn, and you can try our tool, our fancy little robot.
Yeah. We'll make 2-3 minutes of break just to switch for the second presentation, so don't go anywhere.
Dobra, to muszę ekran udzielić.
Możesz na razie tutaj za...
No. Okej.
To co, pójdę chyba ludzi zabrać.
That might be a good idea.
Tak, bo model
Tak, że on tak sobie w międzyczasie po prostu myślał dalej nad tym, co...
Tak, żeby nie było, że wiesz, że wpisujesz, nie dostać odpowiedzi.
No, ja może...
15 sekund, co się dzieje, tak to masz takie, no dobra, coś się wydarzy. I to tak, na rynku też to tak działa, to w naszym trybie, tak po prostu zbiera się kilka słów. To tam, jak są te pakiety, tam też jest zaznaczone, że to jest początek, potem jest koniec słowa i po prostu się czekasz, tam kilka słów się generuje i po prostu na bieżąco.
Right, so please take your seats. And without further ado, we have Piotr Pietrzkiewicz and Łukasz Leszewski from Snowflake. They will present quite a lot of insights from the Snowflake itself regarding data science, data engineering. So let's welcome them with a round of applause.
Hey everyone, thanks for having us and hosting us here, especially we're not from Tree City, so it's always a nice reason to visit you. It's a very beautiful city. My name is Piotr. With me there's Łukasz. We represent a company that's called Snowflake. I think it was not intentional, but the topic of our prelection somewhat connects with the first one that we had about LLMs in general, because we focus more on the real cost. Can you hear me in the back? Should I speak louder? Okay. We try to focus today on the part of a data science work that is generally a whole cost of working on not very scalable environments and working on large data sets, feature engineering things you were talking about. So we will do a helicopter view through a platform that will be very fast. I'll try to answer a question I'm stating by myself, why the platform should be used like ours, and then we will do a short demo of data science capabilities, and Łukasz will deliver this because he's a much smarter guy than I am. And generally, I would start with a joke because I'm always stressed when I'm speaking publicly. So when I'm interacting with LLMs, I'm usually very polite in case they go full Skynet. So it's a recommendation for all of you. It's good to say please when you speak with ChatGPT or something else. So generally, what is Snowflake? We are a commercial product, and this is something I need to state right away. We're not an open source. There was a bunch of engineers that was working for Oracle. There was a Polish PhD that was working on vector engines. And back in 2012, they tried to solve a problem of a very large scale, not only scale of data, but also scale of performance, which means if you're in on-premise forever, you work with solutions like Data's, Oracle's. At the time, they were the right solution, others also, but all of these platforms were struggling with one thing. Generally, it's not easy to scale them. So the idea was to take the best practices of what they learned in on-premise, move it to the cloud, and start to use advantages of the cloud, like basically unlimited capacity of virtual machines, regardless if you go with Azure, with AWS, or with Google, as much of virtual machines they're having, it would be cool to consume them and consume them immediately for the purpose of large analytics or maybe the purpose of large data science, engineering, whatever you need. The similar paradigm connects to storage. Regardless how much capacity or how much of data you have, you would like to scale elastically with your storage. And back in the days, these days, basically, because this is somewhere between 2005 and 2012, we don't talk about these ones because it's already a legacy, but we're under the 3V paradigm, so velocity, variety, volume. So a lot of different data, different languages, no common solution to tackle all these problems, like pay as you go, scale easily, have a lot of storage. So these guys came up with the idea to build one platform that should be able to tackle all of those. And around 2015, there was not many platforms like that. BigQuery was entering the market and they were spinning up. There was us, and everything was a bit behind. And they came up with the idea. I will be going very fast with because there is a lot of marketing blurb and I want to avoid this. But generally, the idea is, regardless what kind of data you have, structured, unstructured JSONs, Parquet, CSVs, audio files, whatever, you would like to store them within one single platform. Why? Because of governance, because of bias, because of fair data. It's easier to track changes. It's easier to assign permissions. It's easier if you store them within one place, and all of the data can be interconnected, can be joined. So if you work with time series data, you would like to connect it with structured data. If you work with unstructured data, you would like to have analysts immediate access to metadata extracted out of those. So that was the idea behind the platform. From 2015, it evolved a lot into different directions than just warehouse. That was the initial case, because these guys that were building the platform were people that were building legacy warehouses. So from the workload, as they are calling it, a warehouse, they moved more into engineering, providing orchestration, automation, storage procedures, UDFs, bring your models to the platform, make it a part of data pipelines. They start to build a seamless architecture that would be available on all of the clouds, looks the same. And generally, the idea was to provide all kinds of languages for the users, because users are not the same. There are SQL users, there are more advanced users that write in R, that writes in Python, that use Java connectors, that create applications. And we would like to serve them all. Why? Because their data is actually in the platform, because this was the whole idea. So if you have all data within the one place, you would like to also serve all kinds of users you have within your company. And this was the idea of what can we build. How this was built, it's a concept that I think whoever works with software knows as 3-tier architecture. We use something similar. So generally, if you think about Snowflake, you see it as a single SaaS solution. So you don't manage it. There is a web page, you enter the web page, you see your databases, you can connect to the URL with your Jupyter, with your dbeaver, whatever you are using. It's dedicated for you. It uses ANSI SQL, it uses Python. So as you would work with transactional data, or as you would work with data frames, you actually interact with the data that is within the platform, that is structured in the schemas, databases, things you know. Now, when you're interacting with the platform, this goes to the top layer, which I'll be not focusing today because it's something we called services layer. So it's the brain of the platform. This is where we are compiling your Python, your SQL into C. This is where metadata is automatically stored. So you put data in, we collect automatically data. This is also kind of a movement where the creators came to senses saying, okay, actually the idea of vacuuming data, collecting statistics, putting indexes, partitioning data is not so cool. Maybe engineers are liking it, but business doesn't like it because it incurs a cost. Someone needs to do it. And instead of focusing on training models, tuning models, deploying models to production, people are spending time on things that are unrelevant. From business perspective, having an index is not relevant. Having an insight or outcome of a query is relevant. How fast, why, what can we do with it? So they compiled a lot of different stuff within the first layer just to automate all of these operations, like backups, like indexes, like statistics, like compression, like encryption. So whatever comes in automatically goes through an engine that makes it more digestible from Snowflake. What happens beneath in these two layers is much more important. The first one, and I'll start from the bottom, is the storage layer. And why I think that's relevant for data science and what Łukasz will be showing you, because on this layer, it's where the scalability of the platform takes place. So why data is touched fast, why can be modified fast, why feature engineering on that platform works, how this interact with data science. So if you think about general data science within its paradigm, usually you would either work on a very large clusters, either in the cloud or on-prem, or in most of the cases, you would be part of something that's called shadow IT. You have your laptop, you have your virtual machines, you take your data in unauthorized way, you load it to the memory of your laptop, you try to do something with it, and then maybe you store the results back within the repository. So quite often, the data as you have it is either not accessible to you as a scientist or an engineer. Who is a scientist here? 1, 2, 3. 4, 5. Who's the engineer?
And 5 hidden, probably.
More. Who is the analyst? 1. Who else do we have here? 2. Data architect. Who else? What other roles we have? Because we have like 30 people and 10 people raised their hands, so we have some other roles here.
Hidden roles.
Hidden roles.
They are working,
Who do we have
working
here?
on shadow IT.
PMs, architects, who? Students. Okay, it's generally so. So, whom of you works in enterprises, not in startups, but in places where you have some governance rules in place? Okay, we have around 10 people. And if you work on the consumer side, how much time it takes for you to get the data you need, actually. So you're performing either received a request to build a report, or you have a hypothesis you need to validate, or you want to do a self-service and create a schema for you. How much time it takes usually?
Depends on the project.
Average. You don't have it on your laptop, I need to add.
Not sure.
Days, hours, weeks, months?
Maybe more.
So if we speak with banks, because sometimes we speak with banks, I'm brag here, a usual project where you have something like a self-service sandbox for a consumer may take up to 6 months, which means I received a hypothesis, I identified where's my data, I need to reach out to the owners of the data, and then I reach out knowing the owners and having permission to IT to deliver that data for me. So it's very convoluted, it's heavy, it's complex. It's not easy to get those. So if you have everything stored within one place, in a format that is micro-partitioned, so very small files that are invisible for you but allow huge concurrency, and you have airbags, so governance rules, access rules in place, you have some kind of enterprise catalog, it's very easy to reduce the time from months to maybe weeks. It really depends on the culture. We may say in seconds, but usually this doesn't happen because there are tickets to IT. People need to work. So this process always stay, but the time can be reduced because everything is one place. When you touch the data, you touch it fast. And now once you store it in the platform, you name it as database, table, you put it into schemas, everything is there. You have the airbag rules, you know what is what. You have dictionaries, not dictionaries like you mentioned it, but business dictionaries, glossaries, things that allow you to work with the data. You need power to work with the data. So imagine you're taking your laptop or your clusters and you assign to each of your users a cluster individually. And this cluster can be deployed within seconds, milliseconds, with the size you need. So if you work with petabytes of data, you may have a cluster of 500 virtual machines. If you work with 100 million rows, you may have just one virtual machine. And the deployment happens in seconds. And the deployment for each one of the users can be individualized. So regarding what workload they're touching, what they are working with, each one of them can have a different sized cluster and can be isolated from other users, which is also kind of a problem that was happening quite often on premises where the evolution was happening. And this was like a second wave of data warehousing evolution, meaning even if you buy a large box, framework, whatever, you have a rack with size of the room. You are still limited by the size of the room, right? If you have use cases that you are piling up within the room, as we are having the seats here, you may have as many people, theoretically, as you have seats. Right? So you may say that.
I'm standing.
If we have, no one confirmed, but I assume everyone understands. If we assume that we want to put analysts on one side, data scientists on the other side, and do some kind of segregation to allow some workloads to run faster than the others, we are still limited. By what? By the size of the room and the number of seats, right? Yeah, one confirmation. Thank you, sir.
But then we can make a data science meetup and we need to kick all the data engineers out, right?
For example. But the idea is we don't want that. We don't want to be limited by the size of that single room. So we isolate compute from compute and compute from storage, meaning if you store everything, it may exist without any compute to query the data. But also if you bundle up all of the workloads, you may isolate one workload from another and assign it right power. So platform like this can scale in multiple accesses. Why it's relevant? Because for data scientists that Łukasz will show later, it's very important to give that one person ability to scale, train, do feature engineering, do data engineering, joining the data without impacting, for example, business. So if we would like him to work on a large data set, we would tell him, go to the other room, take all your belongings, take your tools, and don't interact with anyone else, because the other ones here are representing business that needs to run constantly without a stop. We cannot take their seats because we have exactly as many users as we have seats. So we have a dedicated room for you to do your experiments. And that's the whole idea. So he can do whatever he needs. If he needs bigger room, he goes to an admin, and admin says, yeah, we have a larger room for you. Go there, one floor higher or whatever. So the platform scales by deploying multiple compute clusters, each cluster dedicated for particular workloads, as we call them, but also giving you possibility to decide if you want to have 1 seat or 500 seats per each query or per each task. Train model on 200 virtual machines, do feature engineering on 100, and do pandas just on 1, because this is the need of that moment. I don't want to be limited by that room or be enforced to always be in the room that has a size like this one. Why? Because when I work from 8 to 12, I do trivial things, and one virtual machine is cheaper and better for me. Between 12:10 and 12:15, I'm training a model, and I need 512 for that period of 5 minutes. Why not? Maybe this is your need. And the idea is to allow this and allow users to constantly scale up and down where they need, because your workloads are having nature that changes. Query today is not the same as query tomorrow. Why? Because you have more data. Possibly, maybe there were changes. And aside of this one, there's also another type of scalability, which is out, meaning higher concurrency, but it's not relevant today. So the platform is made out of brain, of compute, where you decide who queries what, how fast, what is the SLA we are agreeing, and general storage. General storage, and this will be a kind of a snooze fest, because for you maybe not relevant, but when we work with the table, to make the table accessible, because also data expands. Like we talked about 3V, what you have today is different than what you had yesterday, and maybe different what you will have in 1 hour. And tables are shrinking and expanding. So to keep track generally of performance and make the performance consistent, Snowflake had to find a way how to make it very scalable for tables, not for compute. So if we have a table with the size of 100 megabytes, and we have a table with size of 1 terabyte or 100 gigs or 1 petabyte, how to make performance the same between the sizes, because something needs to touch that data and work with it. So the option to keep performance inline was to divide the table in a very small chunks. Files are 16 megabytes of size, and each of those files, when you load the data, is created automatically. So this represents rows from 1 to 5, this from 5 to 10, 10, 15. And of course, with the size of the table, number of those micro partitions is increasing, because more files, more data, more rows, more micro partitions. But the engine is smart enough to know which micro partitions it should pick when you're asking a query. When you do feature engineering, when you do selects, when you do pandas, engine decides, oh, you did a where that has an index of from now to 7 days in the past, or maybe where the customer ID is something. So in this case, engine says bypass micropartition 1, 5, 7, 12, because micropartition 2 and 3 are having your data. So it makes the performance consistent, and it basically tricks the platform to use something that would be similar to index. But it doesn't have to be kept. It doesn't have to be maintained. It happens automatically, incrementally, whenever the data comes in. So it's a very cheap way of storing the data and keeping the performance. And why it's relevant? Because when you are touching the data, you are doing it concurrently. For data scientists, it's very relevant to pick a lot of data concurrently and not one file at a time, not serialize your operation, but do a lot of stuff in concurrent, because it's cheaper and faster. What kind of statistics are exposed? Min maxes, these things cardinality, things like that. So the platform is always aware what's in micropartition, what's in your table. Micropartitions are invisible for users. It's just the way how we store files for your tables. You see tables, you work with tables, but underneath, this is how it's working. This is the secret sauce. I'll skip pruning because I've mentioned it. Virtual warehouses, they will be relevant here because this is how you interact with your data. So every user, whenever he/she runs a query, decides what's the context for a query, and context represents what are my permissions and what kind of clusters I will use for that query. Is it extra small cluster, meaning the smallest one, medium, that's 4 times bigger, large, 8 times bigger, or maybe it has 512 machines. And generally we use a naming of t-shirts. So it starts with extra small, goes to small, medium, large, and so on. What's underneath is not relevant. What is relevant is that extra small means 1 virtual machine, small 2, 4, 8, and so on, and it equals power. When the query comes in, usually you would use either an interactive UI, some kind of a client, maybe application, Power BI, Jupyter Notebook. I'm not sure what you're working with, dbeaver, Matillions,
Visual Studio Code.
Virtual Studio, Django, whatever you're going to use, this interacts with the platform using common connectors, JDBC, ODBC, REST underneath. When these connectors, when you are performing the job, they are wrapped into the context, saying, what's my name, what's my password, what's my role, so current permissions, what kind of, or what's the name of an object I like to touch, so database, schema, table, do I want it to join, and what is the warehouse, so the compute I'll be running for that query, which means that you can dynamically either rescale those clusters if you want, or switch between them because there are different patterns depending on what you need.
Yeah, in Snowflake, when we are talking about virtual warehouses, we are talking about computing clusters. This is the naming that we have. So when Piotr says warehouse,
yeah, sorry,
think about compute cluster, 2 servers that is doing the calculation.
And I will explain in a second what does it mean. So generally, you use connectors, you send the query goes to the service layer evaluates, did I reply to that query in the last 24 hours? Did the data change underneath? I need to check the statistics. If statistics for that table are the same, or for that micropartition he tries to touch are the same, I don't need to answer that query again. In return, I will give you something from my cache and say, dude, this was your query in the last 24 hours. Data is the same. Don't ask me again, like have it for free. So the platform returns the cache for free in situations where the data didn't change. When the data changed and has been compiled into C#, it hits something we call virtual warehouse compute for a cluster that has a particular size of virtual machines underneath, and you don't manage that. You just see a virtual machine called finance VM or whatever, and underneath there is a lot of nodes, and that VM performs for you a job. Select on your table, which in the end picks those micropartitions in parallel. What's the advantage of using it is that the bigger warehouse you have, the bigger concurrency and parallelity of these processes you are having. Imagine you are not working with the same data as, or you are working on the same table as your peers. You have 65 people touching the same table. Now, if you would work with a traditional environment, we go to the same issue, which is the size of the room and how much you can squeeze. But if you can multiply the rooms or stream it live, you may have much more recipients of the same data. So what happens here, queries come to the platform in parallel because you have 60 peers. The company hires thousands of people. How large is your company?
50 people.
How many analysts?
Maybe 3.
3 scientists?
No.
Okay, so imagine we have 30, not 3, which would mean that one extra small may not be sufficient for them, and some of them are working on the data that represents sales, the other ones are working on the data that represents marketing. Why not divide them and dedicate them their own power and size? So when you define context is virtual warehouses. Warehouses decide which micropartitions they should pick for the query and how to do it in a scalable way. If the engine decides that warehouses or the micropartitions change and there are new statistics, it will just pick the right ones, as you see, the ones that were deprecated or removed, and new ones are pulled from the storage layer in a very fast way. Now, the whole idea, just to repeat it again, store everything in one place, all kinds of data, and have unlimited power for your operations, engineering, training, SQL analysis, connecting with Power BI. These people don't interact with each other. However, they are working on the same data, which means there needs to be some kind of isolation to give all of them the SLA they need. How you can interact in many different ways. Basically, every connector that is on the market is available. And if there are no connectors, you can compile them into containers and throw them into the platform and run them as UDFs, which means that your logic can be nested within the platform. You can bring your libraries and run it as a part of a regular SQL, because not everyone is data scientist or model developer.
Or you can run large language models as well, right? We had a
yes.
recent meetup. We were presenting something like that, so we can have your own ChatGPT inside.
Yeah, you may bring Hugging Face or whatever comes to the platform and execute it in a way of interacting as a consumer. So you have your model nested as a UDF, you run SQL and you predict something, Boolean or regression or whatever you need, or maybe analyze the sentiment and context of phrases, words. You have unstructured data that would be chatbot recording. So what the chatbot says, it's stored as a varchar or maybe as a JSON, and then use the models to extract the sentiment using SQL. You don't need to be a developer. What kind of value it gives to you? It gives a huge value for marketing or for support people to know to whom reach out. If you're a game developer and you are releasing a new version of your game to your mobile and you're collecting events for every second, and these events are like JSONs, and they represent some kind of feedback where the error happens, like the game crashes, there is pop-up saying, we just found an issue, there is a bug, write something to the developers. Developers can use the models inside of the platform to bring SQL outcomes. So count how many occurrences of something like crash when, I don't know, I picked a sword. This is a trivial example, but represents generally this case. So, so this is it. LLMs within the SQL are very hot right now. The market is going crazy to do something with them. The idea of having LLMs in data warehousing platforms is not very clear because there are problems of
accountability.
Rights, who owns the code, who is responsible for mistakes, who is responsible for retraining the models, and so on. It's not so easy, but generally, this is something we see as a wave coming in. We didn't see it productionalized heavy yet. However, we've seen, for example, LLMs models, so large language model being executed in retail, where people from business are writing in the human language, and in the end, the SQL code is created and the bot basically replies with the outcomes for a human language that represents SQL.
So the SQL, available like NoSQL solutions maybe on databases.
So Snowflake is a database, right? Or multiple databases. So this is one of the languages you can use to interact. So when you have, and we will be speaking this in a second, we will talk about one of the features that is very relevant for the platform and may be relevant for you also. Let me find the right slide. Other slides. So what we are talking about is just a subset of the platform, while the platform is much bigger. It's one platform, and all of these are represented features. We will be talking about a feature called Snowpark, and Snowpark represents, it's an umbrella there. It represents logic protein, so like LLMs enclosed as UDFs, but it also allows you to interact using Python or Java. But generally what happens when you interact using functional languages, not declarative languages, because SQL is declarative, Python is not, is that underneath, we will translate your Python code, if it's not bundled as a procedural function, into SQL. Why we are doing this? Because we found a very optimal way of running something called MPP, massive parallel processing, and using parallel number of virtual machines to pick up a parallel number of micropartitions. So it goes back to the early slides. So you interact using Python libraries you write in functions, but you send the code to the platform. Platform picks your Python, and in the backend, service layer will convert it to SQL. You don't see it, but it's very fast, and it's a very cheap way for us of picking that data and converting it. It's a way of bringing your code to the data, not the opposite. So bringing your data to your laptops and then doing something in your memory. We do it the oppositely. Why? Because it's much easier for you to work if you have access to unlimited performance than to bring large data sets to your local environments, which on one hand violates the security and governance, on the other hand is limited to the size of the room again. So we try to avoid this by giving you, if you decided right now I need 64 terabytes of memory, it's possible by sending the code to the platform, not sending the data back to your environment. Was there a question? Or you were just flexing? Okay, flexing. I think I shouldn't go deeper because I see it's very late and people are already snoozing. So if you have any questions regarding what we will talk about, please do ask. If not, I will give Lucas time to execute a demo, and maybe seeing this in live demo will give you more understanding of what we are talking about. Generally, the way of bringing your code to platform is possible by using that umbrella called Snowpark, and it allows you to compile either your models, your Python pipelines into UDFs or storage procedures and execute it within the platform using SQL or Python or whatever you like. Snowpark, I was mentioning, is doing two things. One, you work with data frames, but in the back we translate it to SQL. You don't know, but it's the compatibility between the data frame API, Scala, Java data frames, or Python is like 90%. So you write functions and engine knows what to do. And the other thing that Snowpark does, it allows you to take your code, bundle it up into a function or storage procedure and execute it in the platform as it is in the sandbox environment. So these things are not translated to SQL, these things are. So if you bring us your model and you bundle it as a file, we will execute it as it is. But if you write a data frame API query, we will convert it in the back into SQL. Lucas, I think I will handle it back to you.
I will cover them
Wake people
later
up,
on.
do some exercises, Kahoots.
Okay, so there is a lot of things in Snowpark umbrella term. So I will be jumping into the demo. I will present you how you can work with Snowflake using Python in particular. But you can also use Java and Scala. You can use SQL. It's a natural language for Snowflake. So let me just jump in as later on. We have a really nice architecture that we haven't covered. This is the news from yesterday. That's Snowflake intention to buy Ponder, who is also responsible for modding. So basically, it's I would say modding is the Pandas compatible framework that gives you the ability to work on multiple CPUs on the machine. So it gives you a lot of speed. Ponder, on the other way, is something like there's something that will provide this Panda API to different engines. So this is quite new and quite fresh, I would say. Okay. Regarding the demo, before I jump in, maybe I will just summarize something that the things that Piotr said with a short demo of the Snowflake itself. So here you can see one of the UIs. Like Piotr mentioned that you can work with Visual Studio Code, with Jupyter's Notebook, DBweaver, any type of tool that use JDBC or DBC REST and so on. But here I'm using the out-of-the-box UI that Snowflake provides, which is called Snowside. I once told the story about the scaling up and down, and I get the question, okay, we know what the cloud is. So you probably know it as well. But the key piece over here is that you really don't need to maintain it. And I will just show you how you easily can create virtual warehouse. So this is this computing engine that Piotr said. So to create virtual engine, you just need to type a name and press create virtual warehouse. And right now it's already started. So it's extra small virtual warehouse, and you can just right now start writing SQL queries. If this is not enough, you can just resize it to extra large, right? And it's right now it's extra large. You can start working on extra large. So there is no like putting the machine down, waiting 5 minutes, turning it on, selecting the machine, selecting the high availability, selecting the storage, and so on. It just works. So
what just happened? So with that simple operation, Łukasz resized from 1 virtual machine to 16 in the back, and the time it takes is like seconds. And also what you see on the on the screen is the name of a compute clusters to easily identify them, because each user needs a context, so needs to know with what he works or she. You have a size that represents amount of power, and you have status, meaning am I running or am I sleeping? The ones that are not in use are automatically going to sleep. The ones that are used are automatically waking up and are awakened just to perform your job, and then they will go again to sleep if they are not needed.
Yeah.
How to control costs when it's that easy to scale?
That's a bug. So everything is governed. You may decide who has access to which one of the compute clusters. You may A, you may not B, but you may C.
You might scale, or you don't.
You may also decide
you might not.
If can scale or not. And there's an easy way of tracking back the cost. So if you work in enterprise and you have chargebacks, you can tag operations per virtual warehouse to easily identify who was running the cost on those.
And we also have the auto suspend mode, so it's automatically, you see, it was default 5 minutes. You can change it to 1 minute. Snowflake is built per second, so if you put the calculation in, and Snowflake will do the calculation 2 minutes 15 seconds, then you can suspend it and you can pay for 2 minutes 15 seconds. And in that 2 minutes 15 seconds, there can be a huge number of queries. There is a concurrency. You can do, Snowflake can run multiple queries at the same time. We are thinking about 8, but it's a default option, but you can change it depending on if the query is light or heavy. You can change it to 20 or 30. And if there will be more, you can also use this multi-cluster feature. So it's a scale out, which Piotr was covering a little bit. So as you can see, the form to create and to manage is simple. You just want the size, want the warehouse, and that's it. And you can just go to the worksheets and go to some kind of SQL. Let me just find.
You don't need to also always work with the UI. If you do things programmatically or from code, everything is configured as an SQL. So creating a warehouse is a command like create warehouse type, extra small, name John, and that's it.
Exactly. Everything that I clicked, you can write in SQL. So if you want to create the virtual warehouse, just can execute the command, and that's it. Regarding the resizing, it's also like alter warehouse. It's large right now. It will execute this query really fast, and then you can just alter it to extra small when it's finished, and then you can suspend it. So it's a SQL-based database. So
also it follows all the paradigms of terraforming, boilerplating environments. So if you have CI/CD and you push down the code, basically everything can be configured externally. So you can send the code to the platform to be executed and attach different processes to it. For example, ServiceNow or whatever company is using.
Yes, and this is like so we work we look like the typical database. So you have databases, you have the schemas, you have the tables, views, and so on, and the storage is completely separated from the compute. So if I want to analyze shift sale, like only for the certain country or the certain city, I don't need the really large computing cluster to do any type of calculation. So I can work with extra small. But when I need to create a model for the whole data sets, probably the extra small will be too small. So I need to scale it up. And scaling up and down doesn't create any outages. So basically you can scale up, all the queries will finish on the extra small, and all new will come to the extra large. And then you can scale it down, and everything will be still running, and all the new will go to extra small. So no outages. Snowflake is automatically in free availability zones, so it's perfectly safe. We have 90 days time travel, so the data is backed up. So basically, you put the data and you just start working with it, and that's it. But this is like to sum up what Piotr was saying. So what I want to show you is how you can interact with Snowflake using Python, and exactly this Snowpark which we presented. So I will be working on the Tastybytes data. So Tastybytes is a global food truck network. They are selling food using food trucks. They have a couple of issues. I don't want to really go into the scenario, but we'll be talking about selling food from the food trucks. and they are located in many different countries, including Poland, in Warsaw, in Krakow. Unfortunately, they are thinking about Gdańsk, right? Maybe it will come soon. What I will be doing, I will be using the Snowpark one-on-one for data science. So Snowflake creates something that is called quick starts. So it's really nice and free repository of tutorials. When you go to the mine particular one, so I have Tasty. I'm using this one. So you can go. You have information how to create condas environment. You will get the predefined Jupyter notebook page where you can run those particular statements as I'm doing. I tweaked it a little bit. I added some extra stuff, but basically, if you want to learn Snowflake or check some kind of feature how to do streaming in Snowflake, you can go here, find the particular and correct quick start, and just start working with Snowflake. You can create your own Snowflake account. It's free. Snowflake gives you $400 worth of credits, and you can create your account and start working with the data anytime.
Everyone can create a trial for free. You just need your email. You don't need to provide your credit card or anything similar. And then if you're working on open data sets, NOMA or whatever comes to your mind, and you want to train, just use trial to test how it works like.
And you can create multiple accounts using the same email address, so you don't need to change that.
Never say this.
We, of course, don't recommend it.
It's forbidden. People that do that to jail.
Employees who talk about it. Okay, so I will be focusing on the Snowpark, and I will be doing two things. First, I will be doing a little bit of feature engineering. So I will create the data frame, operate with it, do some filtering, aggregation, and so on, just to show you that it works exactly like PySpark data frames works. Basically, Piotr said 90. I heard about 95, 98% of percentage of compatibility. So basically, you can change the import PySpark to import Snowpark, and probably it will work, but on the Snowflake clusters, not on Spark clusters.
The idea is here to do the push down. So the company that's being bought, modding, what you do in Python is generally using the lazy method, meaning I'm pushing all the work to platform executes the work for me, and I'm just returning the results for myself to do plots or things like that. So push down is very important context here.
Yeah. Second thing that I will be doing, I will be registering model, and I'll be training that model on Snowflake virtual warehouse using the stored procedure, and then I will create the user-defined function using the trained model to execute it as a function inside SQL statement. So this is the main idea. So what you can do actually in Snowflake, you can do the whole analytical life cycle. So you can prepare, transform data using data frames. You can train. So this you can do the fitting on Snowflake. Then we are working, this is a private preview element, but I hope soon it will be released to public preview. So we will have the model registry where you can register it. Right now you can just save it and store it and reuse it. And you can declare UDF and start doing the inference. You can just basically score your data using that model and create the prediction data set. And this is everything you can do using Python language. We have some additional libraries like ML modeling. ML modeling is just a wrapper for a couple of machine learning libraries like scikit-learn, XGBoost, and I think one more. But probably it will be expanding. So what ML modeling will be doing is basically it gives you the ability to train the model a little bit easier, so you don't need to provide a lot of code. We simplify that, and we also changed a little bit of pre-processing, so we also can do the MPP processing for it, because it is also converted. It can be also converted to SQL, like one-hot encoder, for example. So this will be automatically converted to SQL, so you can use this extra large cluster to run this transformation much faster than on a single machine. Okay, so let me maybe jump to the demo just to present you something before the time runs up. Okay, so first of all, to start working with Python, you need to have your own environment. I'm using Conda environment and creating my own PySnowpark2 environment with a couple of libraries. So first of all, I need to import them. So I will be using pandas, plotly, JSON, and Snowpark. Snowpark just to have a session, some functions, and window function. So first of all, I need to import it. Let me try maybe enlarge it a little bit. Then I need to log into Snowflake. I have multi-factor authentication, so I need to confirm.
What he's doing right now is the context I was mentioning. I think it's where you define so username, password is obvious, but what are my permissions is the role and which compute cluster I'm using right now, which is telling the operation how many nodes you will receive for that query or the next query or next operations.
Yeah, this is optional because each user can have default role and default warehouse, but just to make it super clear, I'm typing it explicitly in the code. So first of all, I need to create data frame. So it's really simple. I just create a session table. Session is already established using those credentials. I'm using the table and specifying the table that I want to load to Snowpark data frame. And Snowpark data frame are lazy. So basically they are not executed until you will explicitly ask, show me the data in my environment. So when I will create it, you run this show, then of course the data frame itself will be executed on the Snowflake side and will pass me only the results. So right now when I go to my Snowflake environment to the activity, I will refresh it. So you will see this particular query was executed from the Jupyter, from my Visual Studio Code. And of course, you can check the whole query profile, for example, check how it works, how the pruning looked like. So I scanned only one micropartition out of 2 micropartitions, which Piotr mentioned, and so on. So everything here is executed on the Snowflake when you ask for it.
As you see here, he's running a table function in one of the blocks above, while Snowflake was seeing it as a SQL code. So he had select star from something, which is basically the function underneath.
So now it's something that some of you who worked on with PySpark it might look familiar, right? You have a select, filter, order by, so additional operation, data frame operation, and at the end I'm using the show. So again, when I can go to the query history because everything is registered, and here you will see the select, from, filter, order by. So everything that was I created using data frame was translated to SQL and was pushed to the Snowflake virtual warehouse cluster. So I'm operating using this element right now, and so it's a SQL. You can check the query plan, so you can see how it is executed. You can here compare. You can push the data frame into pandas data frame. So it's a single operation to pandas. But just to show you that the Snowflake data frame Snowpark data frame doesn't consume any type of memory inside your computer, I ran this calculation. So you can see that Snowpark data frame size 0 megabyte. But when I download it to pandas, it's a local pandas data frame on my PC. And because it's a normal pandas data frame, you can do anything you like with it. So if you were working with pandas, you can start working with it again. You can push some kind of wheres, group bys, window functions, anything, and then grab it, convert to pandas, and just play with it a little bit. So about data exploration, so we have these functions like count. And count, you don't need to wait for it because it is stored on this brain level, on the service layer, so this last layer of Snowflake. So basically, Snowflake knows how many records we have. So we don't need to execute the statement. Snowflake will just give us the result. And even if the warehouse was shut down, it will not be turned on automatically because it will be automatically turned on if we need to execute. But this particular query, it resides in the cache layer, I would say. So you don't need to. You can grab this information anytime for free. You don't pay for it, exactly. So describe. So you can check the basic statistics for it, like minimum, standard deviation, max count, mean, and so on for all the numerical variables and character variables, text variables as well. So right now, what I will be doing, I want to create the linear regression model. So I need to check what kind of variables I have, which are numeric, which are reasonable. Maybe I need to do some kind of like data preparation, remove the nulls and so on. So this is what I will be doing right now. So I have 2 categorical variables, 6, 7 numerical ones. So then I'm doing some kind of data distribution analysis.
What happens here is that he's pushing the operation of calculations to the Snowflake and returns just the outcomes to visualize them on a client side.
Exactly. So like
you save a lot of time, because if you think about Cartesian joins, some extreme maths, group bys, partitioning of data, whatever kind of aggregate functions, maybe geospatial functions, you wouldn't want to do it on your laptop that has a limit of memory. Instead, you're pushing this down for seconds in a very large environment just to get the results back.
That's why you push it to pandas.
Pandas, well, with pandas, it's a bit different because pandas gives you a bit more functions than the regular data frame APIs. Can you ask the question?
Yeah, so if you want to do the Plotly or some kind of visualization, it requires pandas data frame. So
and pandas resides in your client memory, so we convert data frames and push it into memory. But with the new
modding,
yes, the idea will be to trick you into thinking that your data frame has converted into pandas on the client side, but it will be still pushing down to Snowflake. So we are changing this to not force you to pull pandas back to your memory. But generally, pandas is one of the environments or standards people like to work with. So that's why we don't have full integrity with pandas. So it happens on your client side. But with data frames, everything happens on the Snowflake side.
Yeah. So I don't want to go through all of that. So here are some extra feature engineering capabilities. So for example, sliding window. So you can do some kind of partition by calculations, calculate additional average location shift sale, like row by row and so on. You can do the imputation with fill NA function, with column. You can change it with AM to 1 and 0. So plenty of stuff that you...
It allows you to interact, to create your own columns, create your own features, create your own objects like tables and save it back into the platform. And if you imagine that you are pushing all of that code for transformations into the platform, you can do operations on terabytes of data and store it back as a new table, as a new object, without pulling it to your laptop. So without wasting time for moving the data back and forth. And It's very cheap, it's safe, and then actually it's much faster than processing it on anything else.
Yeah, so you can work on gigabyte, terabyte, petabyte of data and just pick up the correct virtual warehouse size. And right now, I did some feature engineering, some data cleansing, and so on. Right now, I'm doing the random split and saving the tables for a train and test. And everything was executed, of course, on Snowflake side. So you can see like create table, insert into, and so on. All of that statements were pushed to Snowflake.
You can also see what's interesting, how large is the code in Python comparing how large would it be to have the same code or outcomes in SQL. Basically, not everything is...
Yeah, like this one. One line, it's a couple of SQL statements.
That's why quite often we see people switching to functional languages, because it allows them to do in one line something that requires, 100 lines in SQL, especially when you have nested queries, a lot of queries nested within the query. Python is much more effective, but in the back, engine will convert it into its own SQL. It looks ugly as hell, and no one who works with data would be proud of this, but it works actually pretty fast.
But Snowflake is optimizing that query as well. So you can send it shit, and it will be under the hood. It will look beautiful.
Generally, negatively impacting the performance.
Yeah. Okay. So I have the train and test data sets. So right now, let's try to do some fitting. So I will create the stage. Stage is just the object storage for saving files, basically. It's a hard drive, yeah. So I'm creating the stage where I will put my model. Here I'm using session file put to put the.
Can you tell what model
Yeah.
you're doing?
Well, this is the linear regression. So here I'm doing the fitting with the feature calls and target call array.
So the whole data set was divided to samples for modeling and for validating. And right now, Łukasz will create a regression model, store it as a file, like Pickle or anything else, send it to that stage, to that volume that was created on Snowflake side.
So right now, I'm actually compiling it. So it's run under the second because it's right now it's on my local environment. And I need to register it on Snowflake side using this session sproc register. So I'm registering this function. It will be called like this. It's a permanent, so it will be pushed to Snowflake and stored as the normal functions.
Every user can use
so every user can use it. And I'm using those packages in this particular function. So when I press run, it will be running under the hood something like create or replace procedure. Procedure will be pickled. So this is bytecode. But it also gives you the information about the source code that was used to create this thing.
So what just happened is he created a model outside and registered it as a UDF. So someone working with Power BI, Tableau, whatever has an option of inserting the code directly can consume that function as it would be already available in the platform. For pipelines, for reporting, for queries,
exactly.
whatever you need.
So you can still continue on the Jupyter Notebook. So you can just call that particular procedure to do the model training and create the model itself. But you can also do it from the SQL. You can use this call sproc, something like this. So either that way or other way doesn't matter because it's already stored as a permanent stored procedure. So anybody can execute it if they have right. We mentioned about Snowflake ML, and I said it's a wrapper to the scikit-learn and XGBoost. So the same thing that I did using this procedure, import scikit, linear regression, and so on, I can do it in a couple of lines using Snowflake ML. So it's just simplified stuff, but basically it's doing exactly the same thing.
But pushing down to the platform, so training of the model happens on the platform side in this case. A lot of operations like feature engineering can be pushed down without entering into pandas, what we were talking about. So it's also
this
kind
one
of approach to give people an option to choose what they want to work with, either with SQL, with pandas, with data frames, train outside, train inside, or maybe use pre-trained models we are having. It's your choice. But generally it should be easy for people and available.
Yeah, so this will create the Snowflake ML linear regression model. But if you will check it under the hood, basically it will do exactly the same thing like we did a couple lines above. So it will convert, create, dump, and so on. So, but it's just simpler. You don't need to write a lot of code and achieve the same result. But at the end, you can just convert it to scikit-learn object and work it as a normal scikit-learn model. And so there's a couple of extra statistics about coefficients, variable coefficients, and so on. You can view the model that is stored on the stage and so on. But let's move further, just to not. I already passed the time, but I'm just finishing. So next one. So I have the model. Everything is trained. So I need to create the user-defined function to do the model inference. So what I'm doing here, I'm declaring the function, actually two functions, load model and linear regression predict local sales. It will be using data frame, so it will not run row by row during the scoring. You can pass thousands of rows to it, and it will return thousands of rows in return. So it will run much faster, basically. So this function loads the model, do the prediction, and return the results. So it's pretty simple function. Again, I need to register it as the permanent user-defined function. and I can do the prediction. I don't want to wait, so I want to scale up my warehouse to medium, so to run it faster, and I can just use this train snowpark def select and call UDF over here to do the actual prediction. And if we go over here to check the SQL statement, you can see here is my function inside plain SQL. So you can use this function in plain SQL, in Tableau or Power BI or DBweaver, anywhere, basically.
Can you quickly explain what was the difference between the Sprock before and UDF right now?
Yeah, the sproc is just a pure Python code executed on the sandbox, on the Python sandbox. It's pure Python.
It's a few operations happening as one execution. So you bundle operations together to train the model, the feature engineering, whatever, do the pipelines. And in the end, the outcome of that sproc would be a file that can be registered as a UDF. So UDF is basically something that's much more digestible for users of the platform. And it can be tabular UDF, it can be vectorized UDF, or it can be scalar UDF. It really depends how you design it and what is the need behind it.
Yeah. So
maybe Lucas, let's not go
deeper. Yeah. So this is exactly the same thing that you can do. I will not run it using the Snowflake ML. So you can just run LM predict. LM is the model that I train above using Snowflake ML. And at the end, you can do the evaluation, but basically it creates, of course, the same results, the Snowflake ML and Scikit, because it's the same code under the hood. At the end, you can visualize it on the map, for example, those results, if you want to predict. And you can use various of tools for it. And one of the tools, and this is the really last thing I want to present, is something that is called Streamlit. So it's a pretty nice Python library, open source Python library that can be used to simply create visualization. It uses something that is called widgets. Widgets are the elements type part of the visualization. It's the elements that you will visualize in the app. So as you can see, you can use the STWrite to write the text, STLiner chart to create the chart, and the elements will be interactive. But how it's connected to Snowflake? First of all, Snowflake bought Streamlit, but it still remains open source as the part. But the second thing that is really relevant is that you can execute those Streamlit application inside Snowflake. And Tasty Byte Forecast over here. So you don't need to provision the infrastructure. You don't need to create the environment to create it. You can write your own Streamlit application inside Snowflake and run it. Let's run it maybe for Warsaw or Krakow. Maybe Warsaw. You can create the shift, pick up the shift and just update and create the running application inside Snowflake. So Snowflake has multiple purposes. You can use it for many different things, including hosting the application. So right now, as you can see, it's a normal interactive map hosted inside Snowflake. And what is coming as well is that you will be able to monetize that application inside Snowflake Marketplace. So you can create your own applications or your own data listings and sell it and monetize it inside Snowflake ecosystem. So that's it from my side. Yes?
So how do you see when the time needed to spin up a cluster? Because you showed the extra large system.
How it works? The question is how it works?
Yeah, how do you see it? Because anyone who works with the cloud partners know that it's not in seconds to spin up.
And this is Snowflake magic. No, there is no magic, unfortunately. So Snowflake is keeping something that is called hot pool of the machines.
We have thousands generally. We are one of the biggest consumers of Azure and AWS, I think comparable to Netflix and everything that you find as large companies.
So we are paying for them, but
yes,
not the customers. Customers only pay for them when they turn it on.
We have a pool of thousands of virtual machines, and when you spin up the cluster, these machines from the pool are allocated to your namespace, and then when you turn it down, it goes back to the pool and it's going through a purge, which is kind of destroying the hard drives and memory for that.
So which parts of Snowflake are open source? The DB
Connectors. So
What was the question?
which part of the Snowflake are open source?
Which part of Snowflake are open source? That's a difficult question because Snowflake is not open source. As I said, Streamlit is a kind of library that is open source. Data frame standard is open
Connectors
source.
are
Contribute to the modeling libraries, for example?
Connectors, libraries, I'm not sure. Connectors, Streamlit, I think Iceberg is open source.
Yeah, and we are contributing to that. So Iceberg is the delta killer.
Parts of those. But for example, if you would be, I don't know, a freelancer or would represent the company and you've created a kind of storage procedure that requires very abstract kind of data set, I don't know, for retail exam, for example, and an input would be customer history time series, you can export the Sprock on Marketplace, as Łukasz said, which means that every other customer of Snowflake can buy this Sprock for you and, for example, train their model because you've created a very universal kind of a logic for training a model.
So VoiceLab can sell your tuned LLMs inside Snowflake. And actually, we are working on with one of the Polish partners that is right now doing the private preview for monetizing the logic inside Snowflake.
Marketplace is having logic, which are UDFs and Sprocks, but also having data. For example, I don't know, MasterCard can sell you information if you're a retailer, what are the segments that are buying using the card and how the transactions are going. Vision sells data about harbors. FactSet is selling information about what is happening on the stock market. So every customer of Snowflake is interconnected. It's a large web. And that logic that seems to be interested, if you can contribute, you can expose it for free. You may decide, like, this is the code on Git, it's for free, you want to use it and contribute, or you can try to monetize it. So
Snowflake itself is not
a simple question, not everything is open source.
Yeah, but there are elements of that are.
Yeah.
And Snowflake is contributing to a couple of projects as well. So if you are really interested into it and want to learn more, feel invited.
You will not be invited anymore.
Feel invited to Build Local. This is the biggest event that we are organizing in our region. It will be hosted in Warsaw because, by the way, one of the creator of Snowflake is Polish.
Yeah.
Marcin Żukowski, and he is creator of Snowflake. Snowflake have the third biggest, we are fighting for the second, but right now it's third biggest R&D centers in the whole world, located in Warsaw. So we have a little bit of Polish roots inside the company. So if you are interested, this is the engineering conference. It's not like the marketing. We are doing marketing conference at the beginning of the year. This one is we are aiming for engineers, data scientists. There will be a hands-on workshops, streaming workshop as well. So there will be additional things about Snowpark and so on. So feel invited.
A lot of machine learning. There are a few sessions about LLMs.
Exactly.
No questions. Okay, let's wrap.
All right, so let's thank you guys. Pizza is ready, so feel free to grab a bite.